Thanks for giving me an opportunity to talk a little more about this stuff. Let's just for a second have a show of hands. Who here has ever seen a proof of Scherer's lemma? Not everyone. Among those voting who raised their hand, was the proof, if you remember the proof, is it the proof where you take A and B and replace them by A union B and A intersection B? Or was it a different proof? So who seems to recall seeing a proof where there's this step where you do some log submodularity or something? Okay, so that was the proof of Scherer's lemma that I was first taught 20-something years ago. And then Jai Kumar came and showed me the correct proof. And really, I don't know if this was Scherer's original proof. I couldn't find it online. I couldn't find the paper online, but his original proof was by induction on the number of times each point is covered, and that's totally the wrong way to look at it. And and if you know the right way, then it's easier to prove other things. So I wanted to show you a proof of the fractional version of Scherer's lemma, which is just expanding on the book proof of Scherer's lemma. But instead, I'll just do a special case, which is what we needed at this point in the talk. So this is going to be a special case of the fractional Scherer, and we'll see how easy it is to prove it if you know how. So we had a ground set, and we had a family of sets, I, J, K, L. And I wanted to impose some consistency. So I took my ground set and I covered it. I partitioned it into 7 parts. And I called these 4 parts script I. And these 4 parts I called script J. And these 4 parts I called script K. And these 4 parts are script L. And so now I'm only going to look, there's a sum here where you have sets I, J, K, and L, and each one of them gets a weight. The weight is the Fourier coefficient. And we can assume that all the Fourier coefficients are positive because on this side of the inequality they're squared. And we can approximate them by rationals, and then we can clear a common denominator. So we can assume everything, all the weights here are integers. And so this is supposed to be on sets I, J, K, L such that their symmetric difference is the empty set, meaning 4 sets such that if you look at their union, every point there is covered an even number of times. But I'm going to restrict only to sets which are consistent with this partition. So if you tell me that I union J union K union L is this, then I already know what I is. I is this, and J is this. And K. So I'm only looking at sets such that if you look at the Venn diagram of those sets, each part of the Venn diagram of those sets falls in a corresponding part of the big Venn diagram. So I'm going to restrict only to those sums. And then I have to show this strange inequality. If you restrict to those quadruples, take the square, it's less than the product of these 4 sums. Sum of fi squared, fj squared, fk squared, fl squared. And here's how we're going to do it.
Now the f hats are just
numbers. They're just positive integers. And what we'll take the log of both sides, and I'll show you the log of the left-hand side is twice the entropy of something. So we're going to define that something. And then twice the entropy of that something is going to be less than the sum of 4 other entropies. The entropy of something coming from here plus the entropy of something coming, and so on. And those 4 entropies they won't be necessarily equal to the log of the right-hand side, but they'll bound it from below. And that'll show us that the right-hand side is greater than the left-hand side. So what are our random variables? And let's just say, for the sake of this talk, that I if you go over the elements of I, you have 1, and then you have 2, and then you have 17, and then you have other. So script I is 1, 2, 17, and some other things. So here's my the random variable. The random variable I'm going to look at is of the form x, ci, cj, ck, cl. And what are these, and what are these exactly? So first of all, I have x1 up to xn. X is a binary vector of length n, and this is just the characteristic vector of some consistent I union j union k union l. So what values can this random variable take? For every I, j, k, and l which are consistent, I look at their union, and I take the characteristic vector of their union. So that's their n coordinates. They tell us for each element in the ground set whether it's in the union or not. And then ci is just going to be belongs to, so I have this, and then ci is just going to belong to the set 1 up to f hat of I, of which I of x. So once I know x, I know the I union j union k union l, I also know what I is. Once I know what I is, I let ci be any integer between 1 and f hat of I. And the same with c of j, c of k, and c of l. Okay, so now it's clear how large is the support of this random variable. It can go over all quadruples, and for each quadruple, I have the freedom I have for ci, cj, ck, cl is precisely this. So that's the size. What's written here is the size of the support. So if I take this uniformly over the support, then what I promised you is true. The log of the left-hand side is precisely twice the entropy of this random variable. Okay? Now, what about the...
Because you took this squared, right?
Yeah, I take the log. I get twice the log of this. Twice the log of the size of the support. Mm-hmm.
And the CIs determine the x's?
No, the x's determine the CIs. Once I know the x's, I know I union j union k union l. And I should have used colored marker for this. And once I know the union, I also know the projections. So once I know x, I know I know j, I know k, I know l. Okay?
But it's important that uniform on the product of those things, right?
Yeah. I said here I'm just telling you what values it can take, and then I'm saying I'm taking uniform on all values that it can take. So then the entropy is just the log of the size of the support. And what you said is true. The size is, well, this is the size. What's inside the brackets here? Okay, what do I have on the right-hand side? What random variables am I going to use here? I'm going to use the following random variables. So I'm writing x restricted to script I. So this is just, I take this vector x1 up to xn, but I only look at its projection on script I. So I only look at the coordinates in script I. Okay? So, so I have, this is the definition of x script I. I take this long vector and look at the window corresponding to the elements in script I. And then I have something I call ci superscript 1 and ci superscript 2. And this is my random variable. And what are what are these two what are these two random variables? They're just the copies of this Ci. So when I know the value of x restricted to I, then I know what I am talking about, and then I take two random variables that conditioned on the fact that I know I already, their conditional distribution is just uniform on 1 up to fi. Each one of them is uniform on 1 up to fi, or the pair is uniform on 1 up to fi squared. And now I have to say two things. First of all, why, and I do the same thing for j, k, and l. So why is this true? Why is the entropy of these four things bigger than twice the entropy of this? And why? So this is y1. No, this is y2, and this is y1. So this is question 1 and question 2. So question 1, I made it 1 because it's very easy. You see, I told you what values this random variable takes, but I didn't tell you its distribution. The distribution is as follows. I take x uniform from here, and then I look at the projection on these I coordinates. So of course, the size of the support is this. So it goes over all possible i's, and for each one, you still have this degree, f hat of I squared choices to make. But why is it not equal to why is the log of this not? Why is the entropy of this not equal to the log? It's just bounded by it because it's not necessarily uniform. Okay, if it was uniform, then so the largest it can be is the log of this if it's uniform, but perhaps it's smaller. So that answers question number 1. And now we reach the crux of the whole proof, question number 2. And what I haven't used here is the part of the hypothesis of Scherer's lemma, or the fractional Scherer's lemma, and that every point should be covered t times, and here t is equal to 2. So when we look at our ground set, every point in our ground set is covered by at least 2 of the sets, script I, script J, script K, script L. And now I'm going to use that. So how am I going to use that? If I write the entropy of x, Ci, Cj, Ck, Cl, it's equal to h of x1 plus h of x2 given x1 plus ... plus h of x17 given x1 up to x16 plus ... all the way to h of xn given all x's with index smaller than n, plus plus the entropy of Ci given x, plus the entropy of Cj given x, plus the, okay, so this is, and let's put a 2 here twice, so everything has a 2. 2, 2, 2, 2, 2. Okay, that's twice the entropy of this random variable. Now, what happens when I expand this random variable? When I take h of x restricted to script I, comma, Ci1, Ci2, that's equal to, well, let me use the chain rule for x script I. This is h of x1. Okay, so that cancels one of the 2 copies of h of x1 that I had. Plus h of x2 given x1. Great, that cancels another copy here. Plus, now comes a subtle point, h of x17 given x1 and x2. Because I'm only looking at the coordinates of x which are in script I. Here I have x of 17 conditioned on all the coordinates up to 16. Here I have it conditioned only on some of them. the more I condition on, the less entropy is left. So h of x17 given x1 and x2 is greater than h of x17 given x1 up to x16. So this cancels this easily, so it brings it down from 2 to 1. And then I continue, and then I have h of ci copy 1 given x restricted to I plus the entropy of ci2 restricted to conditioned on x restricted to I. And I say, okay, here I have the entropy of ci conditioned on x. But the only thing that in x which affects the entropy of ci is the coordinates in I. So here I'm conditioning on less, and here it's actually equal. So I have two of these copies, and they cancel out these two. So it seems I'm off to a good start, but then I say, oh, I've only canceled out one copy of h of x1. How am I going to cancel the other one out? I say, okay, I was only doing a I, but 1 also belongs to L. So when I do the random variable that corresponds to L, then I'll get to, it'll dominate the second copy of h of x1, and so on and so forth. Every element that appears there, I'll get to treat it twice, if not 4 times. So this answers this question, and that's the proof of the fractional Schirr's lemma. That's how the proof goes, and this is just a small generalization of what is the correct proof of Schirr's lemma. Okay, so that's what I wanted to say about this. Just I'll remind you, the context in which we were talking about this was that when you take, I wanted this sum not only with respect to one partition, but I wanted to drop the condition that it's consistent with this partition. And then I said, okay, if you take a random partition, then you're getting the ratio between what you see here and what you really want to evaluate is bounded. But it turns out the bound is exponential in the size of the set. So if the sets are size m, you get some bound which is exponential in m. And if you remember what we were proving, so this is what we were proving. We were comparing the 4 norm to the 2 norm, and if the sets in question, the support of the Fourier transform was of size m, you pay something which is exponential in m. Okay, so that was the first thing I wanted to talk about. And the second thing are there any questions about this?
Yeah. So you had this inequality for a fixed partition, right?
Mm-hmm.
You wanted to turn that into an inequality without fixed partition?
Yes. So I have to count how many times each. If I have a.
The smaller the set is, the more times it appears, right?
No, all the sets are I, J, K, and L are of size m. But then you give me 4 fixed sets, I, J, K, and L. I have to count how many partitions they participated in, and I forget the exact calculation, but the answer is.
This is 128.
What?
It's not a constant. They don't.
No, it's something that depends on m. It's something exponential in m. That's what I'm saying. But what should appear here is so square root 3 to them, but this is somehow a wasteful procedure and gives you a non-optimal constant. Okay, any other questions about this? Good. Okay, then second thing I wanted to talk about was the slides I rushed through yesterday. Okay, so these are the two. Okay, what's on the bottom is the true version of Beckner's inequality, the Bonomi-Gross Beckner inequality that I want to prove. you have two vectors x and y which are epsilon correlated. So y is a noisy version of x. And you look at the expectation of f of x times g of y. F and g are non-negative functions. And the claim is it's bounded by the 1 plus epsilon norm of f times the 1 plus epsilon norm of g. And maybe it's easier to understand it intuitively if you look at the Boolean case. So if f and g are just the indicator functions of some set, so x is the indicator of f is the indicator of script x and g is the indicator of script y, then because there is some correlation between x and y, you expect that perhaps if you can choose x and y such that the probability of x falling in script x and y falling in script y is slightly bigger than the measure of x times the measure of y. So it's slightly bigger than what you'd get if they were independent. But this tells you that it's not much bigger. So if you take a number less than 1 and you raise it to a power less than 1, you're increasing that number. But it tells you if you increase it by this much, then it already dominates this. So it gives you some measure of how much you can make these two things correlate. Okay, so let's see more or less what we have to do to prove this, and how going from this to this is just one more small step for man. Okay, so what we're going to do is something similar to here. We're going to have some inequality and have entropy of something on the left-hand side, entropy of something on the right-hand side. But unfortunately, this time to show this, you have to solve some calculus problem and show that indeed this is greater than this. So it's more ugly. It's not that elegant. So let's see what. So here's what we want to prove. So I write this out. The expectation of this. So I go over every x, give it weight 2 to the n. Then for every x, I go over every y, and I give it some weight depending on how many coordinates it agrees with x and how many it disagrees. So, and then I take the log of both sides and I cancel terms and I get something like this. So here's some expression. A of x and y is how many coordinates they agree. B is how many coordinates they disagree. And you want to give a prize if they agree and a fine if they disagree. And this is what you get. And then, once again, I want to approximate everything by rationals and then clear common denominators. I want to have integers, so I'll have support of some random variable. So after you, so this is what you get after you clear the common denominators, where R and S depend on epsilon. Somehow S over R plus S is 1 minus epsilon over 2, and R over R plus S is 1 plus epsilon over 2. So you get something like this. And then okay, now we can start defining our random variables, and it's sort of clear what random variable you have to choose for the right-hand side, for the left-hand side. So I'm going to choose a random variable x, y, z, and I'll tell you what the support is, and it's going to be, I'll take it uniform on the support, and then its entropy will be the log of the size of the support. So what I need is that x is in script x, y is in script y, and now I'm going to define 4 sets. A00 is a set of size R, A11 is a set of size R, A10 is a set of size S, and A01 is a set of size S. And Z, so X and Y, everything here belongs to 0, 1 to the n. And Zi is always belongs to A of xi, yi. So if xi is 1 and yi is 0, then zi has to belong to A1, 0. So given the fact that xi is 1 and yi is 0, z is distributed on some set of size s. And s is smaller than r, so whenever they agree, you get something, you get more entropy, and whenever they disagree, you get less entropy. And that defines what the support of this random variable is, and its support, the size, this is exactly the size of the support. Okay? So the entropy of that random variable is the log of this. Now, on this side, I'm going to look at the same x and y. I'll take them from this distribution. So I'm taking x and y. Note that if this is uniform, if x, y, z is uniform, it forces x and y to be epsilon correlated. It means that it's more likely to get xi equal to yi than xi different from yi, because r is greater than s. So I'm going to take the conditional distribution of x and y, and those are going to be, this is going to be greater than h of x, and this is going to be greater than h of y. And then I'm going to use the chain rule. So let's see what it, okay, so h of z is going to be equal to the left-hand side, and on the right-hand, this is supposed to be less or equal to the right-hand side. And I'm going to use the chain rule. I'm going to look at it bit by bit, and I'll hope that every bit that I expose here, well, when I do the chain rule, I have to condition of what I've seen. And so far, we're hoping that the conditional distribution is still such that the entropy of the next bit of zi is less or equal to, well, we have n steps here, and every step we get this factor, plus something times the entropy of the next bit of xi and the next bit of yi. And so using the chain rule, so using the chain rule, this is what we have to prove. I mean, at this point, as I told you yesterday, I knew I had to be lucky, because it doesn't have to be true bit by bit. It could be that on average it's true. If it was true on average, I think this proof would be even worse. But luckily it's true regardless of the past. And then, okay, I want to get rid of this z, so I write h of z as h of xy plus h of z given xy, and that makes z go away. And then I get some expression in x and y. And also, there's another thing. Just believe me that if I multiply r and s by any, it only depends on the ratio between r and s. If I multiply r and s by constant, this expression that I want to show that is non-negative stays the same. So here's the calculus problem you get. You have a distribution. This is the joint distribution of xi and yi. And you have to prove this, that entropy of x plus entropy of y times something minus the joint entropy. And then you get some additional factor that comes from the case when x is different than y. The case when x is equal to y was multiplied by log 1, so it disappeared. And okay, and now this is a calculus problem. And okay, so you do some, you have to dirty your hands a bit, but not too much, because everything is very nicely symmetric. So you use the Lagrange multipliers, you get some expressions, and then you start looking what's the best way to utilize them. And so one last thing, I have 2 more minutes, that I'll say is that it's sort of, it's slightly intimidating to solve this unless you already knew what you're looking for. I know that in Beckner's inequality, it would only be equal when script x equals script y equals everything. In that case, xi would be distributed half-half between 0 and 1. Yi would also be uniform on 0 and 1, but they'd be epsilon correlated, and then you'd get this distribution. So if you know what the minimum is, it's easier to try to show that these constraints imply that the minimum has to look like that. So, okay, you play around with it a bit. I'm going to skip those details. And last thing I want to say is what about non-Boolean functions? So, when you have non-Boolean functions, you have to add on another two coordinates to x, y, z. Instead of x, y, z, it's sort of similar to what we did here. You have x, y, z, a and b, where a is uniform on 1 up to f of x, b is uniform on 1 up to g of y, and you have to see how that changes the entropy on the left-hand side and on the right-hand side. And luckily, because you have some kind of homogeneity that this power is 1 over this, somehow it works out that what you add to the left-hand side is exactly what you get on the right-hand side. You use this this nice fact. If you have the entropy of x and you add the expectation of log of any function of x, that's less or equal to the sum of the log of that function on all of x. So that's a fact that's easy to prove, and using that fact, you see that the contributions on the left-hand side and the right-hand side by adding these two extra coordinates are the same. So you go from Boolean to non-Boolean just in 2 lines, and that's it. Okay, that's all I have to say.